Welcome to our lecture on the distribution of inverse F. Imagine you are baking and a recipe calls for 2 cups of flour for every 1 cup of sugar. The ratio is 2 to 1. If we flip our perspective and ask for sugar to flour, it becomes 1 to 2. Flipping the ratio upside down does not change the fundamental relationship between the ingredients. In statistics, we use a similar idea to compare the spread of two different groups. Today, we will explore what happens mathematically when we flip that comparison upside down and why this simple trick is incredibly useful in the real world. Now that we have our baking analogy in mind, let us look at how this applies to statistics. To truly understand the inverse F distribution, we first need to define what a standard F distribution is. In statistics, we often need to compare the spread or variance of two different groups. We do this using an F distribution, which is literally just a ratio of two variances. Specifically, it is created by taking two independent chi-square random variables which measure total spread and dividing each by its own degrees of freedom. Degrees of freedom simply represent the number of independent pieces of information used to calculate that spread. Building on that definition, let us look at the exact mathematical formula. The standard F distribution, which we will call X, is defined as a fraction. On the top, we have U, a chi-squared random variable representing the variance of our first group, divided by its degrees of freedom, M. On the bottom, we have V, a separate chi-squared random variable for our second group, divided by its degrees of freedom, N. If the variance of the first group increases, the overall value of X increases. If the variance of the second group increases, the value of X decreases. This fraction is the exact mathematical definition of an F distribution. This formula we just saw leads us to an important question. What happens if we flip it? We define a new variable y as the exact reciprocal or inverse of our original variable x. Taking the reciprocal means we are just doing 1 divided by our original fraction. By substituting our original fraction into the reciprocal equation, the denominator moves to the top and the numerator moves to the bottom. Look closely at this new fraction. It has exactly the same structure as our original definition, a chi-square variable divided by its degrees of freedom all over another chi-square variable divided by its degrees of freedom. The physical meaning remains a comparison of variances, just viewed from the opposite perspective. Because the structure of our new fraction is identical to the old one, we arrive at a powerful realization. We can definitively state that the inverse of an F distribution with m and n degrees of freedom is simply another F distribution. The only difference is that the degrees of freedom have swapped places, becoming n and m. This mathematical symmetry is known as the reciprocal distribution property. It is incredibly useful because it allows us to convert complex statistical tests into simpler ones just by flipping a fraction. You do not need to learn a whole new probability shape. You just reuse the one you already know. Now that we understand the reciprocal property, let us look at a practical problem it solves. When conducting statistical tests, we use critical values. A critical value is a specific number on a probability graph that separates everyday likely outcomes from highly unlikely extreme outcomes. Usually, we need to find values for both the extreme right side, called the upper tail, and the extreme left side, called the lower tail. However, printing F distribution tables for every possible combination of degrees of freedom for both tails would require massive, impractical books. Therefore, textbooks almost always only print the upper tail values to save hundreds of pages of paper. So, how do we find the missing lower tail values? To find those missing lower tail values, we use a magical relationship derived from our reciprocal property. This formula states that the lower critical value for m and n degrees of freedom is exactly equal to 1 divided by the upper critical value for the swapped degrees of freedom, n and m. Here, alpha represents our level of significance, which is the small area in the tail of the curve. If alpha increases, the critical value moves closer to the center of the distribution. This relationship completely eliminates the need for both tail tables in textbooks. You just find the upper tail value for the swapped degrees of freedom and divide 1 by that number. Before we move on, let us see this formula in action with a concrete example. Suppose you are conducting a statistical test and you need to find the lower 5% critical value for an F distribution. You are given 7 numerator degrees of freedom and 10 denominator degrees of freedom. You look in the back of your textbook, but the table only provides the upper 5% values. We need to find the value F sub 0.95 for 7 and 10 degrees of freedom. Since we only have upper tail values, we write out our critical value relationship formula. We will swap the degrees of freedom to 10 and 7 and prepare to take the reciprocal. Continuing with our calculation, we now open our textbook to the standard F distribution table. We look for an upper tail area of 0.05 using 10 for the numerator degrees of freedom across the top and 7 for the denominator degrees of freedom down the side. The table gives us the number 3.64. We substitute this value back into our reciprocal equation. Now we just need to do a simple division of 1 divided by 3.64. This gives us approximately 0.2747. Physically, this means there is exactly a 5% chance that a randomly selected ratio of variances from this distribution will be less than 0.2747. Now that we have successfully used this formula, let us understand exactly where it comes from. We are setting out to prove the reciprocal relationship we just used. We start with the basic definition of a lower critical value. The probability that our standard variable x is less than or equal to the lower critical value is exactly alpha. Next, we take the reciprocal of both sides inside the probability statement. When we do this, a basic rule of algebra requires that the direction of the inequality sign must flip from less than or equal to greater than or equal to. The overall probability alpha remains exactly the same. This sets up the foundation for our next logical step. Continuing our derivation, we recall that 1 divided by x is our new variable y, which follows an F distribution with swapped degrees of freedom n and m. Substituting y into our inequality, the equation now tells us that for our new variable y, the area to the right of our flipped fraction is exactly alpha. But wait, by definition, the specific number that has an area of alpha to its right is called the upper critical value, written as F sub alpha for n and m. Because both this upper critical value and our flipped fraction leave an area of alpha to the right, they must be the exact same number. Setting them equal and rearranging gives us our final magical relationship. So we have proven that this relationship holds mathematically. Now let us look at what this actually means visually. On the screen, you see two F distribution curves. The top curve represents our original distribution with m and n degrees of freedom. Notice the small shaded region in the far left tail? This area is alpha. The bottom curve represents our inverse distribution, where the degrees of freedom are swapped to n and m. The large arrow shows the reciprocal mapping. The tiny area on the left side of the first curve perfectly matches the tiny area on the right side of the second curve, as long as you take the reciprocal of the number on the horizontal axis. This diagram beautifully illustrates how flipping the fraction shifts our focus from the lower tail to the upper tail. Now that we have visualized the concept, let us apply it to a real-world hypothesis test. Suppose you are comparing the variance of machine A to machine B in a factory. Your calculated test statistic is the ratio of their sample variances, which comes out to 0.20 with 5 and 8 degrees of freedom. You want to test if machine A's variance is significantly less than machine B's variance at a 5% significance level. This is a left tail test. Instead of calculating the lower critical value like we did in the previous example, we can take a faster approach. We can invert our test statistic itself and compare it directly to the upper critical value of the swapped distribution. Continuing with our faster approach, we start by defining a new test statistic, y sub 0, which is the reciprocal of our calculated test statistic. This effectively puts machine B's variance on top and machine A's variance on the bottom. We substitute 0.20 into the equation, giving us an inverted test statistic of 5.0. Because we inverted the ratio, we must also remember to swap the degrees of freedom. Our new degrees of freedom are 8 for the numerator and 5 for the denominator. Next, we look up the upper 5% critical value for these new degrees of freedom in the standard F table. The table tells us the upper cutoff point is 4.82. Finally, we compare our inverted test statistic to our upper critical value. Our inverted statistic is 5.0 and our critical value is 4.82. Since 5.0 is greater than 4.82, it falls into the extreme rejection region on the right side of our new curve. Therefore, we reject the null hypothesis. Physically, we conclude that machine A's variance is indeed significantly less than machine B's variance. By inverting the F statistic, we completely avoided needing a lower tail table and turned a confusing left tail test into a much simpler right tail test. Before we wrap up, let us consider why this mathematical trick matters in the real world. In practical statistics, such as quality control in manufacturing or comparing drug efficacies in medicine, we constantly compare the variances of two different samples. The reciprocal property of the inverse F distribution solves a major physical problem elegantly. It guarantees that software developers and statisticians only need to program or print half of the data, saving immense computational and physical space. Furthermore, it allows researchers to easily flip their perspective. If comparing Group A to Group B yields an awkward fraction, they can instantly flip it to compare Group B to Group A without having to recalculate their entire probability model. We have covered a lot of ground today, so let us review the key takeaways. First, we learned that the inverse of an F distribution is simply another F distribution, just with its degrees of freedom swapped. Second, we saw how this mathematical symmetry acts as a powerful shortcut, allowing us to find lower tail critical values using only standard upper tail tables. Finally, we demonstrated how it simplifies hypothesis testing by letting us convert any left-tailed variance comparison into a standard right-tailed test, saving time and reducing calculation errors. You now have a complete understanding of the distribution of inverse F and how to use it effectively. Great job following along.